Hello everyone, this is Soumya Ratna Devnath. I'm a master's student in the Department of Computer Science and Engineering at the Indian Institute of Technology, Gandhinagar, India. I'm really excited to present our work, L3D-Pose, that is, lifting poses for 3D avatars from a single camera in the wild. 2D pose estimation refers to the process of detecting key points of a subject, such as joints, limbs, or facial landmarks from a given image or video. These key points are represented in a two-dimensional plane with xy coordinates. While 2D pose estimation is widely used in applications like motion tracking, gesture recognition, and sports analysis, it has a fundamental limitation that it lacks depth information. This means that while we can determine the positioning of body parts in an image plane, we have no direct understanding of how far or close these parts are from the camera. 3D pose estimation extends this by adding a third dimension, that is, the depth z coordinate. This allows us to reconstruct the full spatial structure of a subject's movement, providing a more realistic and detailed representation. Accurate 3D pose estimation is crucial for pose retargeting, which involves transferring of an estimated pose from an image onto a 3D avatar. This is widely used in computer graphics, animations, biomechanics, and virtual reality. The most direct approach to achieving this is by extracting the 3D key points from a given image and mapping those key points onto an avatar skeleton. However, this straightforward pipeline faces significant challenges when applied to animals due to data limitation and domain adaptation issues. Unlike humans, which have extensive motion capture data, animals exhibit unpredictable and diverse movements, making large-scale real-world 3D data collection difficult. While synthetic datasets provides abundant level 3D data, models trained solely on synthetic data often struggle to generalize on real-world images. To bridge this, we leverage the existing large-scale natural 2D animal pose datasets such as macaque pose and horses 10K, which contains the annotated 2D key points of various animal postures. We also leverage a synthetic 3D pose data generation pipeline where we create extensive 3D motion datasets using rigged avatars performing diverse actions in a simulated environment. We propose an hybrid framework that extracts the 2D key points from images using a pre-trained 2D pose estimation model. We then lift these 2D key points into 3D space using an attention-based MLP model, which predicts the 3D key points without relying on the image data. Finally, we retarget this pose onto a 3D avatar, allowing seamless animation and visualization. 3D human pose estimation have seen significant progress in the recent years. This is largely due to the availability of large-scale 3D datasets and motion capture systems. Recent research have explored deep learning models such as CNNs, transformers, and graph neural networks to estimate 3D key points from a single RGB image. While human pose estimation is well explored, the same level of advancement is not present for animal pose estimation, mainly due to the lack of 3D annotated datasets for animals. Unlike human pose estimation, 3D animal pose estimation remains an open challenge largely due to the lack of large-scale 3D datasets, the unpredictable animal movements in natural environments, and the difficulties in capturing ground truth 3D annotations. Techniques like AnyPose reconstruct 3D animal poses using multiple synchronized cameras, but this requires a controlled lab setting. Some CNN-based and transformer-based models have been trained on synthetic datasets, but they suffer from domain adaptation issues when applied to real-world images. To overcome these challenges, we focus on lifting the 2D animal poses into 3D using a hybrid approach rather than solely relying on direct 3D pose estimation. 3D pose lifting has been widely studied as a way to infer 3D key points from 2D pose detections. This reduces the need for extensive 3D motion capture setups. Early works relied on geometric constraints and optimization techniques, but these methods were often sensitive to noise and occlusions. more recent approaches leverage deep learning, where multi-level perceptrons and graph convolutional networks have become popular choices. Transformer-based architectures have also emerged, leveraging self-attention for capturing long-range dependencies between keypoints. However, despite these advancements, most of the existing works focuses only on human pose lifting with no dedicated efforts targeting 3D pose lifting for animals, which presents unique challenges such as species diversities and non-rigid motion. In this work, we introduce a systematic approach to generate large-scale synthetic 3D datasets using rigged avatars performing diverse natural actions. We animate the virtual macaques and horses inside the Unity game engine, creating realistic motion sequences such as running, jumping, and climbing. To ensure diversity in the data, we use multiple camera trajectories to capture different viewpoints. We developed two datasets, Deep Macaque and Deep Horse, which include detailed 3D pose annotations tailored for pose lifting and retargeting. We also propose an efficient, image-independent network that lifts 2D key points to 3D space using a simple attention MLP model. Unlike traditional approaches that rely on full image information, our model is pose-driven, making it more scalable and robust to domain shifts. Here's how the proposed method works. We first pass the input image through a 2D pose estimator. This predicts the key points in the image space. The detected 2D key points are then normalized and passed into an attention MLP model. The attention MLP learns the spatial relationship between the key points using a self-attention mechanism to improve the accuracy. The network predicts a soft 3D pose, which represents the initial estimate of the 3D structure. Although the attention MLP provides a strong initial 3D pose estimate, retargeting this into a 3D avatar is inherently ambiguous. To refine our estimates, we introduced a lookup table-based matching system. We pre-compute a large dataset of diverse synthetic 3D pose capturing various natural movements. Given a predicted 3D soft pose, we perform nearest neighbor search in this lookup table to find the most similar deep 3D pose with more key points representing more joints. The final step in our methodology is retargeting this deep 3D pose into a rigged 3D avatar. This involves computing the joint angles between bones to ensure smooth motion transfer, performing texture matching using histogram equalization, aligning the avatar's appearance with the real image, and rendering the avatar in Unity, ensuring realistic shadows, lighting, and motion dynamics. To accurately capture the full body structure of animals, we first need a robust set of anatomical key points. Traditional human pose estimation models typically use 17 to 22 key points, but these do not fully represent the anatomy of animals, particularly for features like spine and tail. Many existing 2D animal pose datasets such as macaque pose and horses 10K suffer from this missing key points, which makes the accurate 3D reconstruction difficult. To solve this, we define a novel set of anatomically significant key points tailored for animals. For instance, in our work, Deep Macaque dataset have 29 key points and Deep Horses dataset have 33 key points. Table 1 here represents the key points correspondence of our dataset with the state-of-the-art datasets. One of the key innovations in our methodology is the lookup table-based refinement of 3D pose. This step plays a crucial role in ensuring that our predicted 3D poses remains anatomically realistic and transferable to avatars. Table 2 showcases the pose-wise average variance of the key points across different animation sequences for Deep Macaque and Deep Horse datasets. To further analyze the structure of these poses, we apply Principal Component Analysis or PCA, which reveals that similar poses naturally cluster together in a reduced dimensional space. This clustering demonstrates that our lookup table-based approach effectively grouped together the related poses. This ensures that given a sufficiently large and a diverse dataset, we can accurately map a wide range of soft 3D poses to their closest deep 3D counterparts. Our quantitative evaluation demonstrates the effectiveness of our attention-based MLP model for 2D to 3D pose lifting and its superiority over existing methods. We compare our approach against state-of-the-art baselines, including graph convolutional network-based methods and MLP-based 3D regression models. We evaluate the performance using mean square error (MSE) and percentage of detected joints (PDJ) at different thresholds. Our model achieves lower MSE and higher PDJ scores compared to prior methods, indicating its improvement of pose accuracy and generalization. Additionally, we conduct an ablation study showing that incorporating attention mechanisms significantly enhances pose lifting quality. Our qualitative results showcases the effectiveness of our approach in lifting 2D poses to 3D and accurately retargeting them onto 3D avatars. As seen in the figure, we visualize the progression of 2D key points to the final 3D pose retargeting. In conclusion, our work presents a novel approach for lifting 2D animal poses to 3D and accurately retarget them onto rigged 3D avatars. By lifting the 2D poses, we have successfully overcome the challenge of limited real-world 3D data. Unlike the CNN-based approaches, our proposed attention MLP model is lightweight and efficient, making it more suitable for real-time applications. Our model is also independent of the image data, making it more robust to domain shifts in natural settings. The quantitative and qualitative evaluations demonstrates that our method is more accurate, efficient, and generalizable for in-the-wild 3D animal pose estimation. This research also paves the way for future advancements in animations, biomechanics, and virtual reality applications with potential extension to more species and real-time motion tracking. Thank you for your attention. See you in ICASSP 2025.